I'm Josh Host. I'm the Executive Director at Internet Security Research Group, and we run Let's Encrypt.
So welcome to our session. We're going to cover some of these items on the agenda just very quickly. We'll talk a little bit about, I'll start off by talking about our relationship with ISRG and the Let's Encrypt team, which has been a really good and fruitful one. Just a little kind of intro section. I'll hand off to Josh for probably the bulk of the conversation, which will be around these items, kind of 2, 3, 4, 5, 6. So TLS overview, some history of web PKI, the background for Let's Encrypt, something about the organization, and a little bit about the future for PKI from the perspective of the Let's Encrypt team. And then I'll close with a short section on PKI from the perspective of post-quantum cryptography, which is obviously an interesting topic that we all have to become more and more aware of and start to address. So let's get going here. Here's the clicker. Oh, I start. Sorry.
I think you're going.
Lack of rehearsal here. So we've had a great relationship with the Let's Encrypt team. We've been both able to help the team with direct contributions, so cloud credits for running some of their infrastructure, some of their critical infrastructure. We also have been able to contribute through an organization we call Alpha Omega, where a number of the large cloud providers get together and collaborate around helping the open source community increase and kind of do uplift around security. Great example of that, another part of ISRG is the Proximo project. So there's a project where we're funding the creation of a lot of critical tools that are widely used in the infrastructure of the internet, in rewriting those in Rust language. So Rust provides the performance of a C, C++ implementation, but with the language and the compiler enforce a number of memory safety and thread safety capabilities, which in the end we believe will result in fewer bugs and fewer security bugs. So that's been a great project. We both use Let's Encrypt for our Amazon Trust services. So we issue, as you know, public certificates. We'll talk a bit more about that. And the certificate transparency logging, we're a heavy user of the capabilities that the Let's Encrypt team has. It's also the case that we get the statistic from you guys, which is that a lot of Amazon customers are users of Let's Encrypt certificates. Even though we have ACM and we have capabilities in this space, it's still super useful to be able to have access to these state-of-the-art capabilities from the Let's Encrypt team, and a lot of Amazon customers are using that, and they can sort of tell by address space like what's coming from AWS and what's being used by their infrastructure. And we'll talk a little bit more about how Let's Encrypt uses AWS. One quick little note, people, just to be super clear, we now just this week launched for the first time the ability to use ACM certificates outside of AWS. So to this point, that was always a feature that was confined to our endpoint. So you could have a free certificate automatically rotated for ALB, CloudFront, NLB, other types of infrastructure that we provided. And we even provided this kind of interesting capability to use our enclaves feature, so that you could deploy a certificate to an EC2 instance and the private key would get automatically deployed into an enclave, and we could do TLS termination in that fashion. But to this week, we've never allowed you to fully export not only the certificate, a public certificate, but also the associated private key to make it fully usable outside of AWS. Customers over the years have said, we love the free certificates from Let's Encrypt, but we'd really kind of rather manage things in a more central way. So now we've enabled this feature, and it's a paid feature, so not free. Still, hopefully reasonably priced and will be useful for customers. And I'll talk a little bit about the end about how in post-quantum world, this is interesting because now customers are accessing a very sensitive piece of data, which is the secret key, and you can now use post-quantum, quantum-resistant cryptography to actually download those keys. We'll talk about a little bit more of that at the end. And main point is the last bullet, which is our collaboration with Let's Encrypt remains strong and will continue into the future. So let's get more into how you guys operate.
Thanks. I'll start by going over a little bit about the basics of TLS security. TLS really provides two different things, authentication and encryption. You need both of these things to have a secure connection. The certificate stuff we're talking about today is about authentication. But like I said, you need both. Authentication is making sure you are talking to the entity that you think that you're talking to. Encryption is making sure that conversation is secure. So you can imagine all sorts of problems if you have one without the other. You could have an encrypted connection that's well encrypted, but you're talking to the wrong person on the other end. Or you can be talking to the right person, but a bunch of people can be listening in the middle. So you need both these things. Certificates are about the authentication, like I said. And the really specific thing that certificates do is they tell you which cryptographic keys you should use for a particular entity. So if you boil a certificate down to its essence, it is connecting a domain name and a public key. It used to be that if you want, so you need a shared secret with whatever server you want to talk to. And it used to be that if you wanted to have a shared secret, if Mark and I wanted to share a secret, we'd have to go find some private room to meet and come up with a shared secret together. And then we would have that. But if Mark and I wanted to create a shared secret when we're thousands of miles away from each other, it used to be there wasn't a great way to do that. Now we have something called public key cryptography. It's been around since I think the late 70s, where we can create shared secrets without ever having met. And in this scheme, you have a public key and a private key. The public key, as you might guess, something you make public. Private, you keep to yourself. So in a certificate, that lists the public key that you should use to talk to a website. We need to make sure that when we issue these certificates, they are matched up with the right public key. So we do this through a process called domain control validation. And control is a really key word here. A lot of times you'll see people either incorrectly or casually refer to the question of who owns a domain. And that is not really at issue in this system. When I use a domain, for example, on AWS, I may own the domain, but AWS is getting a certificate from me because they are the ones who have delegated control of the domain. So we need to just do control here, not ownership. The way that works is through challenges. So we issue a challenge as a certificate authority, and you, as a domain controller, you have to prove that you have control of a domain. So in this diagram, you can see that the web server is saying, I would like a certificate for example.com. And then Let's Encrypt is issuing a challenge. And we're saying, essentially, put a big random number at a path that you would only be able to do if you actually controlled this thing. Then, once we've issued the challenge, the web server has to complete that challenge. So part of that completion is signing an account key, signing a nonce with an account key, and that's what you see at the top here. But you also need to place this random number at a certain path, and then Let's Encrypt will go out and check to make sure that you actually did that. So let's talk about a little bit the history here. We started in 2015. Prior to 2015, the reason that we started Let's Encrypt is that getting and managing certificates was quite painful. And as a result of that, people weren't doing it often enough, and the web was largely not encrypted. It was pretty complex. If you got a certificate prior to 2015, there was probably a lot of clicking around website UIs and using arcane OpenSSL commands to generate a certificate signing request. A bunch of back and forth. It was expensive, tedious. And the result of this is that in 2015, about 39% of page loads used HTTPS. And that's page loads, not websites. Those 39% of page loads are quite concentrated on some of the biggest websites on the internet. The percentage of encrypted websites was far lower than that. We wanted to do something about that. I was working on web browsers back then, and it's frustrating to work on security in a web browser when all the data coming in isn't encrypted. We wanted to get to 90% HTTPS or higher, and we wanted to do it in about 5 years. 5 years seemed like the fastest we could possibly realistically pull this off, and we did not want this to turn into an adoption timeline, the kind of thing you see for IPv6 or DNSSEC, right? That is way too long. We wanted to get this done in 5 years. The roadblock to this was getting and managing certificates. It wasn't obvious to us in the beginning, but it became obvious the more we looked into this. That's what we needed to deal with. The solution that we came up with here was to start a new certificate authority. We thought about all other things we might be able to do to solve this problem. They weren't going to get us to that 90% in 5 years. We needed a new certificate authority that just did things differently from how they had always been done before. In 2013, we started planning this out. In 2014, we incorporated a nonprofit. We had some great sponsors and volunteers and other people involved to help get this off the ground. And in 2015, we issued our first certificate. In 2013, I personally knew very little about building and running a CA, so I had a real crash course going through this. Moving forward to today over time, we started off at no websites, no certificates issued, and today we're up at about 600 million websites, over about 500 million certificates. That works out because certificates can have multiple domains in them, so we can cover 600 million websites in fewer than 600 million certificates. So let's talk a little bit about what Let's Encrypt actually consists of. So Internet Security Research Group, ISRG as we call it for short, is the nonprofit that runs Let's Encrypt. So Let's Encrypt is the name of a service, not the name of a nonprofit. ISRG is a nonprofit, Let's Encrypt is a service. ISRG actually runs 3 different projects. Let's Encrypt is by far the most well-known, but we have a second service called DivvyUp that does privacy-respecting metrics, and a third project that is not a service, but that's where we work on building and adopting more memory-safe software for core components of the internet. We have about 25 staff, and our annual budget is about $6.7 million. Only part of that is Let's Encrypt. I mean, most of it is Let's Encrypt, but not all of that 6.7 million is Let's Encrypt. For Let's Encrypt in particular, there are 12 engineers. There's about 3 or 4 at any given time working on the software for the certificate authority, which is open source. And we've got about 8 or 9 SREs that operate our infrastructure. Those staff are supported by fundraising, finance, legal, comms, HR, and management. For physical infrastructure, certificate authorities actually can't use the cloud. It's not allowed per the rules. We do use the cloud for some systems that are not involved in the actual literal issuance of certificates. So we use AWS for some non-issuance systems related to monitoring and logging and things like that. But the actual issuance happens on our own hardware. It's about 3 racks of hardware distributed across 2 different locations. It's got, the only thing that's different than the usual mix of hardware you would see for something like this, compute, database, networking, is that we use HSMs to protect our private keys and actually sign the certificates. HSM stands for Hardware Certificate Module. It basically looks like a rack server with a bunch of special stuff to protect private keys and handle high-capacity signing. Our physical security is a bit more robust than a typical data center setup. I won't get into the details here, but it's relatively difficult to access our hardware. Like I said before, we use AWS for some non-issuance systems. We use CDNs for OCSP and CRL revocation objects. And we have some accommodations for key ceremonies. So that's where we perform a special ceremony to generate the private keys that are the root of trust for Let's Encrypt.
So before you move on, I have to comment here. So what you said is completely accurate. However, Amazon Trust Services does actually run 100% at AWS. The industry is in a transition period where, physical infrastructure is considered, necessary for certain security properties. And we're in this kind of hybrid state that we actually own all the hardware and the infrastructure that we need to run our CA. So while we haven't yet ever seen an example of other CAs running 100% in the cloud, AWS is able to do that. And we'd like to get to a point where we can convince the auditors in that community that we provide all the necessary security at the physical and other layers to do that. In our case, we use KMS as our fundamental kind of crypto, a fleet of HSMs which are behind our KMS service and so forth. So I couldn't resist jumping up and saying that there is at least one vendor in this world that runs their CA full 100% in the cloud, but it isn't common, and it's probably going to be a journey before that becomes a commonplace thing.
There are certainly times when I wish we had more access to cloud resources, and
we should work on that together.
Yeah.
You should be number 2.
Our software stack, Linux, Proxmox for virtualization. We make pretty heavy use of OpenZFS for a bunch of things. Probably not a shocking software stack. Might be roughly what you expect. We write our own certificate authority software. It's called Boulder. It's on GitHub. It's written in Golang. A lot of other CAs don't write their own software, which is why this is somewhat notable. But we do, because the way that we issue certificates at least was very different from how it had been done before. Though I think more CAs are going to the model that we do, so it's not such a niche model anymore. Another thing that we think about when we think about our infrastructure is memory safety. There are all sorts of ways that you can have security issues in your infrastructure. One of the most dangerous ones is memory safety vulnerabilities. It makes me nervous to see large piles of C and C++ on the other side of a network port or on a privilege boundary. I think there's a lot of evidence to back that up and why that should make anybody nervous. So in part for the security of Let's Encrypt, but also because we want to help everybody else, we have our Prosimo project where we build certain critical pieces of software and functionality in safer languages. A lot of the time for us, that's Rust, but like I said, we also use Golang quite heavily. Most of Let's Encrypt is written in Golang. So we built these 4 pieces of software here. NTPDRS is already deployed at Let's Encrypt. It works great. We have no problems with it. Hickory DNS will be next later this year or early in 2026. Russell's will be shortly after that. And somewhere along the way here, we're going to add sudo-rs as well. So we're very happy to be able to improve our infrastructure by bringing additional memory safety. So the output is this whole system that we've been talking about, the engineers, the infrastructure, the software, stuff like that. We currently issue about 6 million certificates per day. I think there was a day recently where it was 7 or 8 million. It's still growing pretty rapidly. It's 600 million websites covered. It's also growing pretty rapidly. It's not going to be too long until that's 1 billion, it looks like. For revocation, we run a service called OCSP where you can get revocation information. We do about 15,000 requests per second at the origin and 139,000 requests per second at the edge. We're actually turning off OCSP later this year. I'll get into that in a later slide. This number here is just to give a sense of some of the scale. And we also operate certificate transparency logs, and those are used by Let's Encrypt, but also by other CAs. So any certificate authority can submit their certificates to our logs, and then reading is public as well. And that's a place where AWS really helps out quite a lot, because those logs do operate an AWS infrastructure, and it would be tough to do without AWS's support because they're not that cheap to run, which is another thing that we'll get into later. All of this costs about $4.5 million a year. In some sense, that's a big number. In another sense, it's not that big of a number, right? I think there are probably quite a few companies around the world that have internal PKIs that cost less than $4.5 million a year. So we're quite proud of what we're able to do on this budget, and AWS has generously contributed a lot of credits that help us with our cloud run services. So we can talk a little bit about what's coming next. Probably the biggest feature that we've put out there in a long time, and that it will be generally available this year, is short-lived certificates. When we started Let's Encrypt in 2015, it was not uncommon to see certificates that were valid for 3 years or more. That has come down over time, but when we started, we said that all of our certificates were going to be 90-day certificates. There was a range of reaction to that. That for some people, that seemed just like panic level short, like 90 days. Is that even a realistic option for people? The reason we want shorter lifetimes is because if you have a key compromise, revocation of certificates doesn't always work that well. It's not something you really want to rely on. If you have a key compromise, either because you made a mistake or something like heartbleed happens, what you really want is those certificates to age out of the system relatively quickly, because the only revocation that actually works reliably is the expiration date. So heartbleed, I forget exactly what year it was, but it was somewhere around 2015, yeah. People with that had just got a 3-year certificate issued during heartbleed, they're in a tough spot. You can get that certificate revoked, but a lot of people don't check revocation. It's a fail open system. We don't want people to be in that position. And if you're going to automate all your stuff, then it doesn't really matter. If your computer is getting the cert for you, it doesn't matter whether it renews every 90 days or every 6 days or whatever. So what we would say to people who are concerned at the time about 90-day certificates is that this is not a certificate authority for people who want to manage certs manually. If you want to do manual certificates, like maybe you can do that on a 90-day cycle, but you are not the target audience for this. We really want people to move to automation. It has so many advantages. So 90 days gets people better security, and it really pushed people towards automation. Pretty soon, we are going to make 6-day certificates generally available. We have issued some production 6-day certificates, but we've only issued them to ourselves for testing purposes. Pretty soon, there will be an allow list and then general availability. There's a feature called profiles introduced in the Acme specification where you can say which type of certificate you want. Up until now, there's only been one option. You get one kind of certificate from Let's Encrypt, and that's it. That's going to change with profiles. There will be a default if you don't select anything, but you will be able to opt into 6-day certificates, and that is a big change for us. It's the first time we've ever issued a certificate that wasn't 90 days. It changes a lot on our end in terms of volume. I mentioned before that certificate transparency logs are not that cheap to run, right? They have to ingest every certificate. Well, once a lot of people start using 6-day certificates, you're issuing a lot more certificates to serve the same population. So for us, we need to get ready to issue billions of certificates if this is what the future looks like. So internally, we spend a lot of time thinking about what that looks like. What does that mean for our database? What does that mean for our certificate transparency logs? Things like that. The next thing that's coming out around the same time as the 6-day certs is IP address support. Today, you can get a cert for a domain name. Later this year, you'll be able to choose domain names and or IP addresses. So you will not have to have a domain name in order to use HTTPS with Let's Encrypt. To be totally honest, I'm not really sure how popular this is going to be, but there are definitely some people for whom this is going to be valuable. It may turn out, a few years from now that IP address certificates constitute, 1% of our issuance. That seems believable to me. It also seems believable to me that it's a much bigger number. I think it's going to be the most popular for sort of infrastructure use cases, IoT, and other things where humans are less involved in the loop because domain names are ultimately a convenience issue. Computers don't care, they just want the number. So we'll see how this goes in terms of popularity, but we've heard enough important use cases for this that we want to make sure that we support it. Did you want to jump in about IP addresses?
It's an interesting phenomenon that, for many of these decades, IP addresses were essentially represented a host, and therefore if you had dynamic infrastructure, you might reuse an IP, but it was kind of, there was some kind of risk in that. But as cloud technology has evolved, at least that's what I know well, IPs have become kind of more of a virtual thing. Like I can reassign IPs dynamically between hosts, for example, with an elastic IP. I can bring my own BYO, bring your own IP, your own CIDR range, and that you can assign willy-nilly to infrastructure. And then we have virtualization of IP as kind of a feature for some of our services, like our Global Accelerator service gives you what are called anycast IPs, which is a router conspiracy that tells the world that, hey, you want to reach this IP address, come here. And that is around the edge of our network, so we attract traffic. And those IP addresses are yours for as long as you keep that accelerator alive, and they don't change. And similarly with network load balancer, some of it in our NAT gateway, these are services in which an IP address represents kind of an object in the system, and we take care of keeping that stable even though the underlying infrastructure changes, even though there might be 25 hosts that we do ECMP across all those hosts with that single IP address. So that's not maybe directly related to how often the certificates will be useful for IPs, but I just thought it might be worth mentioning that the kind of the role of IP addresses, especially as you say, like in these IoT or machine-to-machine scenarios, is kind of changing. And if you want to potentially use IP addresses for kind of long periods of time and still have control over those and use those to kind of expose or consume infrastructure, it's a pretty reasonable thing to do these days.
Yeah. So the reason IP address support is coming now and not a lot earlier is because we did not want to offer IP address certs for 90-day certificates. IP addresses tend to be, in general, more transient than domains. People buy a domain, they own it for years, maybe longer. But IP addresses people often have for much shorter periods of time. So we don't want to issue a certificate to an IP address and then have that IP address belong to someone else during the lifetime of the certificate. So we are only going to be offering IP address certificates for the 6-day certificates. If you get a 90-day certificate, this will not be an option. What Mark is talking about here is that essentially that with AWS, IP addresses don't have to be so transient, which is a nice feature of the system. But for us, we're only offering them in short-lived certificates.
Yeah, that actually reminds me of something else which we didn't talk about when we were rehearsing, but I'll mention it anyway. This is actually an abuse pattern we've seen historically, is people will they'll cycle through IP addresses on our platform looking to try to get one that someone else was using recently, and then see the traffic that may be accidentally coming to that. So we've actually introduced a bunch of technology to sort of have cooling off periods for IP reuse. So it's very much less likely today that you can ever get an IP that was recently used by someone else, and it's essentially to deal with that transient problem. But it totally makes sense to me that we're talking about automation scenarios, and short-lived certificates make sense, even given what I mentioned earlier about how IPs can be useful and can be relatively stable over time if you use the features in the right way.
Yeah. So this I alluded to before. OCSP is a protocol for checking whether a certificate is expired. And the way it works is there's a URL in the certificate. You can make a request to that URL and we'll return a signed object that's specific to that certificate that will say this is revoked or this is not revoked. This has been around for quite a while. It's been the most common, normal way to do it for a while. But it has some problems. The number one problem is that it is a huge privacy risk. So if someone is out there browsing the internet, if you're browsing the internet, if you send an OCSP request and say, hey, tell me about the revocation status for example.com, you're basically telling the certificate authority that you're about to visit example.com. And then when you go to the next website, you do another revocation request, and you're telling the certificate authority again, I'm going to visit this other website now. We don't want that information, and you should not want to give it to us. The way it works now is we just drop those. We don't keep any record of OCSP requests. We drop that data. But we don't even want the opportunity for abuse here. We don't want people's essentially browsing history broadcast to us. So we want to get rid of this system in favor of something called CRLs, or Certificate Revocation Lists, which is just an object that says, here's the list of all the things that we've revoked, and you can see if what you want is in that list or not. And that does not have the same privacy risks. So the main reason we're going to turn this off is privacy risk. The second thing here is that it's expensive to operate. I mean, we're a nonprofit, we try to be efficient. I mentioned before that there's, so much traffic happening here. 84 billion OCSP responses per week right now. That just goes up over time. It's expensive to operate. We don't really want to do it when we have CRLs, which are a better solution anyway. It also, interestingly, takes up most of our HSM capacity. So every time we need to do a signature as a certificate authority, that happens on an HSM where the private keys for the CA are stored. Signing certificates takes up something like, actually issuing the certificates themselves is like 15 or 20% of our HSM capacity, because those certs get signed every 90 days. OCSP gets re-signed, I think, every 3.5 days. So the vast majority of our signing capacity is devoted to these objects. And we'd rather not do that. Well, let me say, it's going to get turned off in August 2025. I'm pretty sure August 4th is the date. We've already removed the URLs from the certificates, so the traffic is already dropping off. But once the last certificate that had a URL expires, then we'll turn the service off. We don't really expect much disruption, but we'll see what happens. So Acme renewal info is a feature that we already have, but I bring it up because it is not very popular yet. Not enough people are using it yet, and it's really important. And it's really important because this is a huge part of how we're going to make the web PKI more resilient. There are reasons that certificates have to be revoked by the certificate authority, not because you as a subscriber want to revoke them, but because we have to. So it could be security incidents, could be compliance incidents, who knows what else. When we have to do that, it is very painful because we have timelines on which we have to revoke this stuff, and it's hard to reach all the people involved and get them to take action before that timeline hits. So if we have 24 hours or 5 days to revoke a certificate, that might be 1 million certificates and 1 million different people. It is very hard for us to contact everyone and get them to take action. Acme renewal info is a polling system where your system will reach out to us. Could be as much as every few hours or as little as once a day, and say, should I renew my certificate early now? And if we know that we're going to revoke your certificate for some reason, let's say we're going to revoke it 24 hours from now, we will sort of flip a bit so that when you check, we'll say, yes, please renew right now. Then you can renew before we have to revoke your old certificate. And this scales really well. Worst case scenario, we're revoking 500 million certificates if we make a big enough mistake. That is hugely disruptive to the internet. It's going to be hugely disruptive today, and it will be tomorrow. And really the only hope we have for making this not hugely disruptive is to make Acme renewal info much more popular than it is now. So I would highly recommend that if you are running your own certificate client, that you find a way to use Acme renewal info so that if we have to revoke your certificate someday, you can sleep soundly, your computer will just take care of it, you don't need to worry about it, no disruption. So this is a really important, but it's something people are not well enough aware of. We're also evolving our transparency logs. There are 2 different kinds of logs out there now. The older style is called RFC 6962 logs. The new style log is called a tiled log, and the formal name is static CT API. And the reason that we're doing this is that we want to make these logs easier and cheaper to run, and we want to make them more reliable. The reason that we want to make them easier and cheaper to run is not just because we want to spend less money or use up fewer AWS credits. It's because we want there to be more of these logs in the world. Right now, not enough people are running CT logs, which is an issue for the ecosystem. And the reason people don't want to run CT logs is because it's very expensive. No one wants to spend hundreds of thousands of dollars a year running a log. So we need to make them cheaper so that we have more of them, and that is better for the ecosystem. We also need to make them more reliable. So we run tiled logs already, and we are planning to shut down our old style logs later this year. For most certificate consumers, this is not going to be something you need to worry about, but it is an important event in the ecosystem. So let's talk about what the problems are with RFC 6962 logs. First of all, they require large and expensive cloud-managed SQL databases. That's the way that we do it anyway. It's the way that I'm quite sure most of the other major providers do it as well. These databases can be relatively easily overwhelmed by dynamic queries. In other words, the people who are querying them are giving all sorts of different query parameters, which makes the results very hard to cache, or not really cacheable at all. So they get quite easily overwhelmed. The third point is what I would say the most serious issue here, which is something called a maximum merge delay violation, which is when a certificate gets submitted to an RFC 6962 log, the log doesn't necessarily integrate that certificate into the log immediately. It instead issues a receipt and says, I promise I will integrate this certificate within the next X hours, where X I think is usually about 24 hours. And then, if the log violates its promise to do that, the log is considered non-compliant and is taken out of the ecosystem, which is both disruptive and means we have one fewer of these precious CT logs out there. So the maximum merge delay introduces the potential for maximum merge delay violations, which is a huge problem. So we'd rather have logs that don't have this going on. The new transparency logs don't have dynamic queries. You don't give it a bunch of parameters and we do a big SQL search and put together a result. We publish very easily cacheable tiles of data. They just exist on S3. We create the tiles, we write them to S3. And we don't have to run these big expensive databases to back the whole thing. It drops the cost massively. They also integrate certificates in batches, and there's no more max merge delay. So the cost you get here is there's a little bit of latency increase between when you submit a log, or when you submit a cert to a log and when you get a receipt, because it does need to actually integrate it first. But it means it's not making a promise, therefore there is no promise to violate, and we don't have these uptime issues because of that. The new logs, we don't have enough operational experience at scale, and the ecosystem doesn't depend on them yet, so it's hard to say for sure what the final cost would be. But it's about an order of magnitude less costly to operate than the other ones. So if you were spending, $1 million a year running a log or $100,000 a year, it's like 10% or less to run the new style logs, which is great. And hopefully that will encourage a lot more people to run them.
Could I ask a question about that? Is it fair to say this is a classic distributed systems move of pushing some of the complexity out to clients? When you have millions of clients, they can do a little bit more computation, and especially for the easy queries, it's super easy for them to do the computation. And if they want to do complex queries right now, they're able to push the complexity onto you as the service provider, whereas now they would have to do a little bit more computation locally to check the validity of the Merkle trees, blah, 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 but there's millions of them and there's only a handful of the backends. So I think it's very reminiscent of what often happens in distributed systems is like, hey, make the clients do more work because we can scale more effectively that way.
Yeah, I think the RFC 6962 authors had their heart in the right place where they're saying, let's make this really easy for the consumers of CT logs. But there just ended up being so much burden on the CT log operators that nobody wants to operate them, and they are pretty cagey. So post-quantum cryptography comes up a lot in the PKI world. There is no support for it in the publicly trusted web PKI today. In other words, there are no publicly trusted certificates that are using post-quantum algorithms. There are a bunch of reasons for that. The biggest one is that the rules don't allow it yet. Right now, the priority is on TLS handshakes, which is not a web PKI thing, but the idea is that when you do the key exchange in TLS, you can use post-quantum The reason that matters, well, we'll get into more about why that matters later.
Talk about that.
So when is this going to be a thing in the web PKI? So the community needs to have an agreement on a plan. So what algorithms are going to be used? Is anything else going to be different? Then once we have an agreement on a plan, it needs to result in a change to the rules that allows post-quantum signatures. But also, because all of our signatures happen inside of HSMs, we need HSMs that support post-quantum algorithms. And not just that they support them, but to support them at a large enough number of signatures per second. So often in HSMs, for example, they'll support a bunch of different signature types, but some of them are hardware, they have hardware support, and some of them are just software support. So the ones that are just in software have like 100 signatures per second, and the ones that are in hardware can be like up to 10,000 signatures per second. We need hardware. So for some people at the scale of like AWS, maybe they have, I'm certain they have access to a lot more HSMs than we at Let's Encrypt do. So they can maybe afford to pile them up and do that kind of thing. At Let's Encrypt, we do not have access to those kind of resources. We need our HSMs to pull a lot of weight. So we need HSMs with hardware support for post-quantum that can do somewhere in the ballpark of 10,000 signatures per second so that we can realistically roll this out to everybody. HSMs are not a piece of hardware whose ecosystem evolves quickly. So the lead time, who knows when HSMs will support post-quantum at fast enough signatures per second, and what is fast enough is different depending on who you are, right? Yeah. It's quite different for Mark than it is for me.
And there's a whole ecosystem around like FIPS validation that has to be updated. So all the laboratories that validate the correctness of the behavior of the HSM. So there's a lot of work to be done here. So.
Yep. So to wrap this up, some recommendations: protect your private keys. That is like the golden rule in the web PKI ecosystem. Don't commit them to GitHub. Protect your keys.
Don't store them on your laptop.
Yeah. Automate your issuance and your reissuance. So if you're ever manually getting a cert, think hard about how to get off that train and get onto the automation train. And the last one here is try to use Acme renewal info. On a day-to-day basis, it may not seem like it makes a big difference, but it eventually will. Every CA makes mistakes. We want to be resilient when that happens, and Acme renewal info is the way to do that. I'm going to turn it over to Mark, who's going to talk a little more about post-quantum now.
Yeah, thank you. So let's talk a little bit more about this fun topic, and we'll back up and say, like, what are we even talking about here? Well, many years ago, academic mathematicians and cryptographers postulated and seemingly have proven that if someone can invent a sufficiently powerful quantum computer, then a lot of our current infrastructure that we use for encryption is in danger. So in particular, the elliptical curve, the RSA technology, these asymmetric PKI type of signatures could be brute forced with a powerful quantum computer, and that creates a problem for us, right? Because brute force attacks currently are just require way too much computation to be successful. As mentioned at the very beginning, today we use symmetric encryption typically for local encryption, disk, database, and so forth, using the same key to encrypt and decrypt the data. But almost all of our network scenarios involve this asymmetric cryptography because they have this beautiful property that we can encrypt something without sharing a secret with each other. And that's critical for kind of bootstrapping. What happens inside of a TLS session, as you probably know, is one of the first things that happens is we exchange a symmetric key so that we can encrypt very efficiently, but the outer envelope has to be done with the asymmetric technology because that way we can encrypt without sharing secrets. Therefore, because there's a probability that at some point in the future, experts disagree, could be 5 years, 10 years, maybe 3 years, probably somewhere in that range, worst case 3 years, best case, depending on your perspective, 10 years. There will exist such computers, quantum computers, which will put at risk our current asymmetric cryptography. Now you may say, well, if they don't exist until 5 or 10 years from now, what are we worried about? And that leads to this classic kind of threat model that has been developed as people have thought about this problem, which is sort of the long-term confidentiality of these network sessions that are happening today. So today we have the TLS connection between a client and a server, traveling across often public networks that are reasonably secure, but you can't ever say for sure that there's not any way for some sufficiently resourced and motivated actor to get access to the encrypted packets as they flow across our public networks. The threat would be that if today someone were to harvest and grab a copy of all those packets and store them somewhere permanently or semi-permanently on a disk drive or a database somewhere or a giant object store, then in the future, once a quantum computer exists, you could take that recorded session, crack that outer envelope of the PKI using your quantum technology, grab those symmetric keys that are kind of the very first thing you'll find inside there and that can get rotated through Diffie-Hellman, et cetera, but still, once you kind of get that outer envelope broken, then you can begin to read all the data inside those sessions. And therefore, when it comes to the TLS world, we're trying to get ahead of this problem, and that's why the focus of the cryptographic community and of governments and others and concerned about some of these issues has been to let's first deal with that sort of TLS handshake and build quantum-resistant technology into that. And then as time goes by, we can go to these other topics because that is more of a real-time attack. Like I can't emulate your website 5 years in the past with a quantum computer, right? I can't pretend to be Google and have a fake certificate 5 years ago. So once the quantum computer exists, then those threats become real. Namely, I could create a fake version of some authentication material and fool you into connecting to me thinking I'm someone else. So that risk will exist once quantum computers exist, and that's why the web PKI community has to solve the problem before the quantum computers exist, but it's not as pressing in those scenarios, again, because they don't have this property of store now and crack later, which does exist for network sessions. So what are we doing about this? As I said, the good news here is asymmetric crypto is at risk, and sometimes when you talk to your colleagues about this, you're like, oh no, quantum computers are going to break everything. No, it's not everything, but it is something important, which is asymmetric. Symmetric crypto is, as far as experts are able to tell today with their analysis, it's not. You can speed up brute forcing of like AES 256, but it's only by a factor of 1,000, which isn't nearly enough because it's super, super resistant to brute forcing. So that's not an issue. Now, the good news here is the industry and the community has gotten together, been working on this problem for a number of years. There was a kind of a de facto international, I'll call it a beauty contest for like, hey, let's get all the world's best cryptographers together and have a series of submissions and analysis and come up with what we believe to be good solutions to this problem. It was actually run by NIST in the United States, the National Institute for Standards and Technology, but it had very strong international flavor, and I'm not aware of anybody, even some of our governments who are not so friendly to the U.S. who are complaining about that. It's been a very international process. And NIST now has standardized on a couple of the early versions of this, including a technology called ML-KIM, which came out of the Kyber submission. And this is now kind of the standard for doing post-quantum cryptography on the web. Now, so another good news here is that I've already implemented in our production systems the option to negotiate a post-quantum algorithm if you want to connect to us over a TLS protocol. I don't have the statistics for how often that happens. I think it's probably super rare because your client obviously has to support this as well, but it is an option. And another really good news here is that we're open sourcing all the work we do in this area. So we are developing with a broader community the post-quantum algorithms. We're integrating them with our open source TLS stack, our S2N stack. We're using formal and also another open source library we have called libcrypto. We are using formal methods or formal verification or what we call automated reasoning to build a formal model of the correctness of these systems and logically prove the correctness of the code that we're writing. And every time a developer does a code check-in and then tries to make improve that code, we run these proofs against the check-in. So we've made the formal methods into very much part of the whole engineering process. So all these things are good and allowing us, I think, to get ahead of it. You might say, well, why those particular services right now? Or why not EC2? Why doesn't EC2 have PQC? Well, first of all, it will have pretty soon. We're actively going to be pushing out the post-quantum TLS across all of our API endpoints and over the next 6 to 12 months. The ones we focused on now are the ones where you can interact with us with very sensitive material, and ACM is a great example. This week, we launched the ability to export X509 certificates. Part of the API is to, hey, give me my secret key. And that's a pretty sensitive piece of data. So you can use the post-quantum algorithm for that API call, maybe just that API call if you want to. So we've implemented that on these three services. KMS, Secrets Manager, where again, you send us secrets or get secrets from us, and ACM. But it will become very generally available across our API endpoints. Again, I mentioned earlier that it's not as urgent for the X509 certificate case because the kind of store and record and crack later scenarios are not possible. So we have a little bit of time to get that done, but we'll work together with you folks and others around the world who care about security on the web, and we'll solve that problem, and hopefully in time before the quantum computers arrive to make our lives a little more difficult. So I think that's it for our session. We thank you very much for your time. Appreciate you spending that with us, and also for coming to Reinforce. And we'll hang around a little bit and take your questions afterwards. Thanks so much. Appreciate it.